So there's some good questions on number 28 about throwing this switch. I'm going to go over part A because I'd want you to be able to think about part B on your own. If you have other questions about that, feel free to email me or I'll make a separate video. But if you really understand what's happening in part A, then part B is just another application of that. So you really want to hold yourself to say, to make sure you're not just saying, I can watch the videos and get it. You should be able to do part B on your own. So let's take a look. We've got this battery and then this one light bulb and then these other two in parallel and then this. Right now, these are on. Things are flowing. There's a complete loop to go from the positive to the negative, and we've got current going through this bulb and then these two bulbs right here. If I could simplify this circuit right now, and let's say this is a resistor R, and resistor R, and shoot, let's not make it R, let's make it easier on ourselves. Let's just say this is 10 ohms, 10 ohms, and 10 ohms. This simplifies to a light bulb that's a 10 ohm light bulb, and then right here, got a 5 ohm light bulb kind of going on like that. That's the equivalent of those two in parallel. And at this point you should feel pretty good about resistors in parallel. 1 over 10 plus 1 over 10, 1 over that is 5. And the question says, what is throwing the switch gonna do here? Because this switch, after all, is here and about to be thrown. So the reason why it's good to do that is because I want to see what's happening with the potential difference in these circuits. And if this is epsilon, let's just say it's 12 volts to make the numbers easier. That means that 8 of my volt drop happens here and 4 of my volt drop happens here. This is 2/3 of the total resistance. This is 1/3 of the total resistance. This gets 2/3 of the total volts. This gets 1/3 of the total volts. You could also simplify it down to 15 ohms and do 12 over 15 is the current and bring it back up and figure that out. Pause this video and do that right now until you feel good that this is 8 volts and this is 4 volts. Coming back up here, I can say, you know what? That's still 8 volts. It's the same light bulb. And this is 5 volts, and this is 5 volts. So that's what our current situation is. 5 volts, 4 volts, 4 volts, and 8 volts. Now we're going to throw this switch. That changes something. We have now put just a wire in this with no conducting or no resistance. It's an ideal conductor, it says in the problem. So all the charges are now going to flow through this way, and none are going to go across the resistor. Given the choice between this resistor and a wire, every single charge chooses the wire. It's infinitely more conductive, so it carries infinitely more current. And so all the current's going to go through here. That means that these two light bulbs are going to go out and have no current across them and have no potential difference across them. All the potential difference will now be this one, essentially throwing the switch looks like this. I've got 12 volts right here, and then I've just got one light bulb. So it's now 12 volts. So this one's going to decrease to 0, and this is going to increase from 8 to 12. And that's the thinking here. So we made this problem easier by plugging in numbers like 12 and 10 and drawing out pictures to figure out what's going to happen in this circuit. These are huge thought problems that really show if you know what you're talking about with circuits. So hold yourself to that level and go on to problem B and solve that. If you can't solve problem B, come back here and work through A on your own and not just watch the video and watch me do it. Make sure you can do these on your own. These problems show up a lot. All right, good luck.